The title of this paper is MemGPT Towards LLM as Operating Systems. Now, this paper came out of Berkeley. I'm fairly sure it is Berkeley. Yes, Berkeley, and was it was quite an eye opener. I'll give you the context of this paper. When it came out, we had significant problems with LLMs. Those problems haven't gone away. One of the problems with LLM was that the input that you could give to the LLM was finite. It was the prompt context window, what they call, right? The size of the context window, and it differed. There's a chart here that shows how much it is. The context tokens that you could give to different models is given in this table that you're seeing, and it's been getting bigger and bigger. Now Gemini 1.5 has practically a million or million and a half as a context window. But when this paper started out, there were inherently most LLMs that you and I can afford in-house had limited context window, right? And now one of the value proposition of agentic reasoning that I've been mentioning is, with proper agentic reasoning and multi-agent collaboration using relatively modest LLMs, you can be at par with the latest and greatest of what are called frontier models, right? And even beat them, right? So the magic is in careful reasoning and collaboration and teamwork, right? So context window size was one limitation. Despite what people say, that limitation has not gone away. People say, if I have 2 million context window, does it not therefore obviate the problem of limited context window? It does not, because 2 million is a drop in the ocean compared to the size of knowledge that you often expect the LLM to dip into and get answers from. The success of the RAG as a dominant Gen AI use case is a testament to how much that is true. You have corpuses of billions of images, or repositories of billions of images, videos, and corpuses of millions of documents. A lot of those documents, furthermore, are proprietary, confidential. You have to be able to dip into it. So the context window becoming larger doesn't necessarily solve all the problems. Yes, you can shoehorn a lot into the context window, but remember, still 1 million, 2 million are the limits today. Whereas the total number of tokens, total number of words that you may have in your document store could be in billions of tokens or hundreds of millions of tokens or whatever, a pretty large number, especially if you're dealing with data that lives off databases and so forth. Or you're dealing with images and you're using all sorts of multimodal learning. So that is one aspect. The second problem, which is quite a bit improved upon, but still is mentioned when this paper was written, is that of uneven attention to different parts of the input. This is an experiment that is done with human beings and has been known in psychology for a very long time. If you tell somebody a lot of facts and ask them to remember it, quite likely they'll remember more of what was in the beginning and what was in the end and lose a lot in between. You can try this experiment with just name of vegetables or something like that. And you can see that most of us will pay a lot of attention in the beginning, and after a little while, our buckets are full. And then towards the end, there's a little bit of transactional memory that's holding on to what came in the end, right? So beginning and ends are remembered. The middle sort of escapes, right? It doesn't get as much attention. Now, that problem is to a large extent solved with all this new frameworks like rope and all of these ideas coming up. Nevertheless, it's not completely solved. It is still uneven. And the third issue is, even if you could shoehorn, let's say, 1 billion tokens into an LLM in the input, do you really want to do that? Because now that machine has to scan through 1 billion tokens. Can you imagine how many batches of data will go into that machine, or how much data? And if nothing else, it will have to linearly study every token before it can answer your question. That speaks to the latency, that speaks to the compute cost. As a minimum, it's an order n cost. In practice, it's an order n square cost, somewhere between n and n square, right? Very expensive. So those problems remain. In other words, memory problems remain, right? Context window. Now, what this paper says is something quite interesting. It says that, now, wait a minute. In traditional computer science, all of us have taken courses. If you come from a computer science background, all of us have taken courses on operating systems, right? Even if we have not taken, we all know that a processor, for example, has a very limited L1, L2, L3 cache, right? It works, the arithmetic logic units, they work, and the pipelines and schedulers and everything. At the end of the day, they're letting the processor work with what is inside the processor, data that's inside the processor. If a data is not found inside the processor, it doesn't mean that the processor gives up. It just goes out and gets the data from main memory, right? Which is far less expensive. Inside the processor, you're talking about SRAM, very expensive, on the die memory, extremely fast retrieval. But if you don't get it, then you come down the memory hierarchy to cheaper memory, namely your DRAM, right? DDR, whatever, DDR5 these days, for which most of us are sitting upon, what is it, 64 or 128 GB on our laptops or workstations, right? So that's a pretty vast amount of memory. But if it cannot be fit into that, for example, you might not want to fit all of Wikipedia into the main memory, potentially, because you might be doing other things on your machine. So then there is always the disk storage, right? Nevertheless, a processor works seamlessly with data, irrespective of where it is, isn't it? A good program execution involves getting the data, loading the data first into memory, from memory into the caches, and then internally doing the computes on them. That's what it is, isn't it? And that's the notion of how an operating system works. So the question they asked is, they thought about this, a brilliant idea, brilliant insight. They said, why don't we think of engaging with the LLM as analogous to an operating system? Just as an operating system has a core, a CPU, which inherently has very little memory, a very short space of data that it is literally has access to. But all you do is you have a whole hierarchy of memories, right? Main memory, disk storage, from which we retrieve when needed the relevant facts and load it into that. In the same way, let us think of the LLM as the processor, as the CPU, right? And just as the CPU internally has a cache, a very expensive cache, memory that's premium memory, right? The SRAMs. In the same way, let us treat the context window of the input to the LLM as that cache. Does this make sense, guys? If we treat the context window of, like, so what it means is, here's the processor, you're going to send it a prompt. So the analogy is, here's a LLM, you're going to send it input in a prompt. Prompt is of limited size. This is very analogous to, in the CPU, in the caches is this much data. That is what you're going to feed into the arithmetic logic units, your registers to add, subtract, and whatever, right? And then in analogy with the CPU, if something is not found, there must be supporting system, a support system that will go get the information from the storage, one of the storages, memory or disk, right? Likewise, the CPU should have the ability, if it computes something or has something, it will both read and write from storage. So you need a way to store things there into memory, external memory, and the word they use is external context, right? And get things from there as needed. Now, the good thing with LLM is then once it gets that, it can understand what it retrieved. So this is somewhat like very in a microscopic way. It is doing RAG right there. Um, it is a form of RAG in some sense, right? It is doing that, but in a very very tightly integrated manner. That's the main idea. But if I could do that, why is this relevant? What it does is it makes an agent highly capable. When the agent, at this moment, what happens is, have you noticed that if you're chatting with an agent, a chat agent, it has a finite length of conversations. After a certain time, it will say, and even with these frontier models, you must have noticed after some time, they say, all right, you have exceeded the max length of the conversation. It used to happen. I don't know if it still happens, but even a couple of months ago or a month ago, it was still happening, right? Um, if it has stopped happening, one of you can enlighten me on that. But you do exceed the maximum conversation length. Why do you exceed the maximum conversation length? Let's think through that. The reason it happens is the entire conversation is in the memory and has to be essentially part of the prompt. It has to be shoved into the context window, into the input, before the next question of the user can be answered. And there is a, and so there'll essentially be an overflow sooner or later, right? And so now, if you think of a chatbot as one agent talking to you, what would you like in a good agent? As always, take an anthropomorphic point of view. What would you like in a good friend of yours? Two things. If your friend is advising you, you would first want that the friend remembers all that you talked so far, right? You don't want it to be like Dora, like every time you meet the person says, "Oh, what? So how should we proceed? Let's start from the beginning on this problem." You wanted to remember the conversation that has happened, but that conversation may be pretty long and involved, right? Take the example of your making the business plan. If you are making the business plan, then you are inherently, obviously you're not having a short conversation. You're predicating the next 7 years of your life on that startup idea, isn't it? So 7 years, give or take a few more or less, is at stake there, in which you'll work day in and day out, and other people will trust you and join your team and work day in and day out for pennies in the hope that the idea works. So your business plan better be a good business plan. Common sense, isn't it, guys? And so there will be a lot of give and take, lot of debate, lot of partial conclusions, intermediate results that you will have in the drafting of the business plan. And there, remembering the context and the conversation that has happened and the ability to summarize it is crucial. Let us look at the second part that is essential. You would also like your age, like if you're talking to your friend or some expert and getting advice or doing back and forth conversation about a business plan, you would want the person to be sufficiently well versed in business plans, isn't it? But the literature on business plans and business strategy is vast. There are literatures pertinent to strategy analysis. There are literatures pertinent to team dynamics and leadership. There is literature quite pertinent at that moment to the finance of it, coming up with a cash flow analysis for your business, and literature pertinent to the market analysis, advertising strategy, sales strategy, and so on and so forth. And each of these are vast rabbit holes of knowledge, isn't it? You can keep going down the rabbit hole. So what you would like to have is somehow that your friend, at least, or your friends who are guiding you, they have access to that vast amount of knowledge. They're not just making things up. They're able to search, they're able to get results, and they're going to do that. So keep that context in your mind as we read through this paper. I think once you get that whole context, I think it's a straightforward paper to read, but of very influential. Now, what has happened is, as this paper, just to give you the end result or the impact of this paper, after this paper came out, MemGPT guys, these people who wrote the project, have created an open source project called literally MemGPT agents. You could use that. I strongly advise you to go install MemGPT agent and start talking to it. You'll get a flavor of it, right? And you'll get a bit more flavor. It's very easy. It's just a pip install, literally a pip install py memgpt, I believe, right? And then after that, you just fire up the memgpt start, right? And it will fire it up, and you can start talking, and you'll get a flavor of it. Perhaps we'll do it towards the end of this session today itself. Remember, at this moment, so this paper, when it came out, all the other people like Langchain and other guys who are doing agentic frameworks, they all started incorporating this idea. In fact, this paper was very, very influential in reiterating the enormous importance of memory in solving complex problems. That is a seminal contribution that came out of it. Are we together? And memory management, the summarization of things and conversations, etc. There are a lot of good ideas and gems in this paper. So let's get through this. With all this preface, I do believe that it might be a relatively straightforward read from here onwards. Large language models have revolutionized AI, but are constrained by limited context windows, hindering their utility in tasks like extended conversations and document analysis. We spoke literally about these two use cases a moment ago, right? And now, when this paper initially came out, and since then, some water has flown down the river. And so you may say, well, context window limitations are not that big, but I hope we have argued successfully that it will always be a limit, because no matter how big you make the context window, data and knowledge is growing exponentially relative to it. To enable using context beyond limited context windows, we propose a virtual context management. So those of you who are familiar with the word virtual memory management will immediately see a complete parallel here. Operating systems work by doing a virtual memory management. And here they're saying virtual context management. Context is memory in their interpretation, right? We propose virtual context management, a technique drawing inspiration from hierarchical memory systems in traditional operating systems, which provide the illusion of an extended virtual memory via paging between physical memory and disk. This perhaps needs a bit of explanation. See, what happens is that, let's just take main memory. Suppose your main memory is just 32 gigs. And you read a file and load it into memory, which is, let's say, 40 gigs. Have you noticed that the machine is magically able to do that? And the reason it's able to do that is assuming that you have allocated some swap space, or what in, I think, some operating systems are called virtual memory, I believe. Right? What you do is you apportion a part of the hard disk as a spillover space. Right? And so it loads some things into memory and some things spills over into the virtual memory, right, or the swap. So, and then you page in and out. The part that is relevant and being used, you keep in main memory, and the parts that are not being used goes over to the virtual or in the disk. These days, actually, I would slightly change it. I think a closer analogy could have been between the cache of the CPU and the main memory, paging things in and out. Right? Because the cache is really limited, and no machine ever works simply by doing everything within the cache. Right? I mean, very few things can be done. You keep paging in and out between the cache, the CPU cache, and the physical memory. And so perhaps that could have been a better analogy here. We'll continue this. Using this technique, we introduce MemGPT, Memory GPT, a system that intelligently manages different storage tiers in order to effectively provide extended context within the LLM's limited context window. We evaluate our OS-inspired design in two domains where the limited context windows of modern LLMs severely handicap their performance. Document analysis, where MemGPT is able to analyze large documents that far exceed the underlying LLM's context window, and multi-session chat, where MemGPT can create conversational agents that remember, reflect, and evolve dynamically through long-term interactions with their users. Then they say we release the code and data for experiments at blah, 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 right? If you go there, you'll also see that now it's an open source project and you can install it, the agent, and you can play with the agent. So much has happened since the publication of this paper. In recent years, large language models and their underlying transformer architectures have become the cornerstone of conversational AI and have led to a wide array of. So I'll skip some of these. I've explained this, but I suppose this sentence is important. In MemGPT, we treat context windows as a constrained memory resource and design a memory hierarchy for LLMs analogous to memory tiers in traditional OSs. Patterson's, by the way, is the classic book on computer architecture that almost all of us have, I suppose, either been delighted by or suffered through in our undergraduate. Go ahead. Yeah. I really appreciate so that everybody can hear.
In this paper context, if I'm been implementing with a RAG, the memory or the kind of the tokens which are part of the RAG would be in this context, or it is only that user prompt context?
So, no, actually what they're saying is when you look at the document part, it looks very much like RAG.
RAG is also part of it.
So how does it differ? That's what I said, that the document part is very analogous to RAG. It will retrieve it from that. But the important thing is it isn't just retrieving and then asking the LLM to interpret it. It has more going on in that. Think of it as this. It is a more structured way of ragging onto the document.
Right. If I take a practical example, I gave that the content which has been more relevant to that my questions, the content which is there in the RAG or my vector DB.
Yeah.
Okay. So I'm assuming that whatever the prompt I'm giving it, which is in the context of the RAG content. So when it is sending it to that, either it is a GPT-4 or whatever it is, and then you're at what part of this information will be sent it to as a whole context to that.
Yeah. See, when you RAG, almost all the search results are bundled inside a prompt, right, and shipped over to OpenAI, shipped over to GPT.
Yeah, GPT. Yeah. So that is also part of the context.
That becomes, in fact, their definition of context is that which goes into the LLM.
Yeah, right. Good. Thank you.
So that's that. So guys, those of you who are remote, were you able to hear the question?
Yes, Asif.
All right. So I suppose it's delightful to see this figure one. I really liked it, how well it works, because as they say, the proof of the pudding is in the eating. The way this thing works is because LLM is understanding how the conversation is flowing, in a way, it can do things that a dumb processor cannot do. It's observing the context of the conversation very intelligently. So here's the conversation. It says, how was your day today? So the user answers, fun. My BF James baked me a birthday cake. So I suppose if you do a conversation like that with a normal LLM, you will get the response, oh, wow, happy birthday. So far, so good. And here comes the crucial thing. Right at that moment, let us say this is too short a conversation to have memory pressure, but assume that there was memory pressure, right? What this machine does is it sends an alert to itself. saying memory pressure. Now, do you remember we talked about instruct, function calling that these things can do? So the LLM can now function call. What it will do is it will do a function call by saying there is a working context there. Let's append the information, which is that birthday is February 7th. How did it come up with birthday is February 7th? Current day. Exactly. Right. So it says birthday is this and boyfriend named James. Right. These are the two precious nuggets it needs to remember. And the way the prompt, the machine is structured is it pulls in these nuggets, things that it doesn't know and that may be valuable, and saves it. And do you see the difference from RAG? It is not. It's creating. RAG is just retrieval from a document store. Here in the conversation stage is creating facts and storing it. Right? Yes, that's right.
Wouldn't Asif, wouldn't LLM also understand this context even though it is not retrieving it?
No, the LLM is understanding it,
Yeah.
Chitu. It is the LLM understanding it. But the important thing here is the LLM will make no effort to store it in any external storage, such a fact.
Okay. Got it.
These people store it in an external context, namely in a file system or in a database or something like that.
Mhm.
Then let's see how the conversation flows thereafter. Did you do anything else? Yeah, go ahead.
Question, Asif.
Uh,
So,
Yeah, good.
one basic question is, yeah, it looks very obvious that birthday is February 7th and boyfriend names James, right? But if I were implementing it, right, what kind of prompt would I need to basically extract that information from that sentence?
Yeah.
Blue.
So the actually the in the if you go to the project, they show you all the prompts. The system prompts are very well done. It's all there. You can see it. It basically says extract nuggets of information, roughly speaking.
Oh, really?
Yeah.
That's it?
That's it. It's not. It's not.
It's not specific or
No,
anything.
no.
It's just.
And we'll get to that. When we go to the appendix, we'll see some of these prompts in a moment.
Okay.
Right?
Yeah,
So
because
no-
that part was magical to me.
Yeah,
I didn't know how
that
it
is
was
right.
done.
No, that is easy with the LLMs now and good prompting. You are in the prompting course, right?
Yeah.
The LLM. So yeah, by now you should be an expert at it.
Yeah.
So here we go. So now you say, okay, what's the big deal? All that the LLM did is function calls to extract nuggets from the conversation and save it. Right? So what's the big deal? Here's the big deal. After that, the conversation flows and then it says, let's look at figure 2. Did you do anything else to celebrate your birthday? And let's say she says, yeah, we went to Six Flags. And now LLM doesn't know what Six Flags is. So immediately it goes to its storage and says, okay, search for Six Flags. And when it searches for Six Flags, what it says is, oh, in the past conversation, now look at the 3 lines. Those are log traces, right? Conversation. There was a trace on 1st of January, 24th of January that said, LOL, yeah, Six Flags in some context. Second one was on 14th that said, I love Six Flags, been like 100 times, right? And the next is, James and I actually first met at Six Flags. Now, for a moment, imagine that this recall had not taken place. And what is given in black on the figure 1 also wasn't there. Birthday is February 6th is not there. Boyfriend named James is not there. Right? At that moment, it might not have been able to give this answer that you see the machine give. The machine says, did you go with James? It is so cute how both met there. Right? So do you see the whole point? You cannot have this kind of a conversation with a regular agent because this thing remembers the history of your conversations and from that is able to have a far more meaningful conversation with you. I hope this illustrates or brings home the power of this approach. And it's good that this figures are right at the top so that it brings home the point. So how do they do that? Now the question is, we do see that this approach works, isn't it? And this is the way you should have your conversational agents. Now the question is, how does it work?
Okay, you're going to explain how it works, but first we do in figure 1, we do working context.append, right? Working context, I think, is the stuff that goes into the prompt.
Yeah.
But then when we are reading it, we are saying recall storage, which is more durable storage, I guess. And
Yeah.
we are doing a search on that. How did the stuff from the working context get into the recall storage?
Oh,
It-
you keep
it-
flushing it.
We
So
have
that is-
to,
That's the
it's like a
architecture. will come.
buffer that keeps written,
Yes, yes.
getting written, right?
Exactly. And
Okay.
that's exactly what you will see. In fact, quite literally, it's a good segue into how this works. So let's look at it. So here's a preview of the picture. Right. So you can see, I'll come to that. Actually, you can see that there are all of these queue managers, recall storage, archival storage, etc., etc. And it gives you some insight, but let's read through the description carefully because it's a short paper. We can very carefully read through this. MemGPT's OS-inspired multi-level memory architecture delineates between two primary memory types: main context, analogous to main memory, physical memory, RAM, and external context, analogous to disk memory, disk storage. Right. Main context consists of the LLM prompt tokens. So main context is what you shove into the LLM to get an output. Anything in main context is considered in context and can be accessed by the LLM processor during inference. By definition, right? If that is the input that goes into an LLM, the LLM is seeing it inherently. External context refers to any information that is held outside of the LLM's fixed context window. This out of context data must always be explicitly moved into main context in order for it to be passed to the LLM processor during inference. So the thing is, you will accumulate a vast amount of information. You need to be able to search and find the relevant bits, just like a operating system does. MemGPT provides function calls that the LLM processor to manage its own memory without any user intervention. Is there something weird about this English sentence? MemGPT provides function calls that the LLM processor to manage its own memory without any user interaction. The sentence is grammatically, to me, doesn't make sense. But what he is trying to say is, because LLMs have function calls, ability to call functions, therefore, MemGPT leverages that and uses that to move things between the conversation, between and the context, and the external memory. The prompt tokens in MemGPT are split into 3 contiguous sections: the system instruction, the working context, and the FIFO queue. So let's think through what it is. See, guys, you have the LLM. Let me just take this. Imagine that you have the LLM, right? You have so much space. This is the max number of tokens you can send in. For the machine to work, some part is just basically your program, right? Your system prompt. That you can't change because that is driving the whole machine, isn't it? It is very much like in your normal operating system. Your code compiled is sitting there, right? So it is there. Now what happens is, it also needs to remember a little bit of the conversation. Does that make sense? The last few records, it should remember. So what you do is you create a FIFO queue, first in, first out. Right? So suppose, what is a FIFO queue? Let's say that it has, let me just say 5 slots. 1, 2, 3, 4, 5. Right? So what it means is, at any given moment, it will remember only the last 5 relevant facts. As an example, or maybe 50. Let me just make it 50. Last 50 relevant facts. So you need to, because that will be relevant to continue the conversation. You stick it in here, right? And then the rest of it is your context, like anything else that you may load. Like this is this is your FIFO, right? And then the remaining space in between, let me see, is where you'll do the magic by loading other facts that may be relevant, that you are bringing in from storage, right? Think of it as doing a RAG from storage in some sense. So let's look at the architecture from that perspective. The last 5 things that happened, right? Last 50 bits. Yeah, either user prompts or the machine may have injected some important pieces of information into the context, right? So whatever it is, or alerts or whatever it is, right, for LLM2. So this is it. And now look at this picture. Now, does it make sense? Look at this. This is what is going in the prompt tokens. System instructions, of course, you can't do. It is your program in some sense, right? Then the queue contains certain relevant facts that are brought in and out. And then there are read-write functions which can basically retrieve the necessary information as needed. Right? So this is it. What you're saying is, I will divide the input space into 3 buckets and fill those buckets carefully. Then what will happen? This will go into the LLM and the LLM will produce output tokens. What do you do with the output tokens? Make sure you store that also, isn't it? Because it's a conversation, right? Now, if you maintain a queue, of course, somebody has to maintain the queue, do the eviction, and store the things from the queue into a recall storage, right? So this paragraph is this figure is worth reading. It says a lot. In MemGPT, a fixed context LLM processor is augmented with a hierarchical memory system and functions that let it manage its own memory. The LLM's prompt tokens inputs or main context consist of the system instructions, as you saw, working context, and a FIFO queue. So FIFO queue are facts, right? The LLM's completion tokens outputs are interpreted as function calls by the function executor. MemGPT uses functions to move data between main context and external context. What is the external context? Here and here, right? Anything outside the prompt tokens is the external context, right? So the LLM can request in immediate follow-up LLM inference to chain function calls together by generating a special keyword argument. For example, request heartbeat is equal to true in its output. So for example, if you really want more things done to answer your question, it can keep calling itself. So this is just the mechanics of it. Function chaining is what allows MemGPT to perform multi-step retrieval to answer user. So it may get something and then realize, oh, but I need some more. I have a different question to ask. And then the LLM will ask, and then so on and so forth. So let's read this now.
What is the difference between the archival storage and recall storage?
Recall storage is pretty much things that are happening. See, from the FIFO queue, right? You have just pushed it there. And it hasn't reached archival storage. So think of it like this. Documents are things that are facts, right? That are immutables. You put it into the archival storage. Generally, you don't expect it to change. But recall storage are things that may change. For example, as you will see in the example given in this paper, the boyfriend changes. So you will have to go edit your recall storage. That is one of the things. So look at this conversation. Look at figure 4. It says, how the machine asks, how is James doing? Any special plans today? So remember, 1 week has gone by. That was February 7th, right? And well, as you know, 1 week is an eternity for the young. So February 14th. How's James doing? Any special plans today? Well, actually, James and I broke up. What does the LLM do? It's a crucial fact. So it does a, do you notice that it does a basically an upsert operation or update operation, isn't it? It replaces boyfriend named James with ex-boyfriend named James. And response, sorry to hear that. Hope you're okay. Right. So guys, I can go through more details about it, function execution, etc. There's more there, control flow and function chaining and experiments. Let's look at the way the generally deep memory recall. See, it works very well where you need to remember long conversations, right? So that is the deep memory recall, DMR performance. And clearly, MemGPT does very well. Interestingly, you notice that MemGPT, its numbers are unbelievably high compared to even the state-of-the-art model, GPT-4 Turbo. At that moment of the writing, GPT-4 Turbo was the state-of-the-art. And do you see accuracy of 35% versus accuracy of 93.4%? That's a game changer, isn't it? Guys, do you realize that if I were to ask you a question, do you remember, yesterday, remember the movie we went to? And you say yes. And 2/3 of the time, you remember completely a wrong movie, or you don't remember the movie at all. I would be pretty annoyed, isn't it? What kind of a friend is it? Right? He doesn't remember anything that matters to me, or something like that. On the other hand, if your recall is 93.4%, that's pretty good, right? Yeah. And that is the value of it. Yeah. Rausch L is a metric. It is again a recall metric. No. It's a recall metric. And again, there is no doubt. So what happens is you will notice that for all of these tasks, right, there are no perfect metrics. So people often use a combination of metrics, right? Accuracy simply means how accurately you recalled the right fact, as opposed to not recalling or recalling the wrong. Rausch L is a little bit more complex. So, and so it goes. I can go. Now, you notice one thing, that what you can do with conversations, of course, much more easily you can do with documents that have already been shredded and put into your archival storage, isn't it? You ask it a question, it will, like, for example, here is a lovely one. Look at this, figure 5 and figure 6. Document QA performance, right? Clearly, you can see that MemGPT, it takes a little while to realize that the line for MemGPT is up there. I don't know. It almost seems like it is just the boundary of the chart, way up there. Accuracy, right? Just about everything else does badly. Right? You cannot use just an LLM to do this. And again, this goes back to the fact that, see guys, agentic reasoning is careful reasoning. It is dividing a task into smaller tasks, doing it, planning it, doing it systematically. So from that lens, if you look at this paper from that lens, this MemGPT is a very systematic, organized way to address a conversational context, isn't it? Yeah, this is it. So look at figure 6. So I'll just read this point because this point is important. MemGPT performance is unaffected by increasing context length. Why? Because it doesn't care, right? Yeah, because it has saved all the facts somewhere else, right? On the other hand, traditional methods obviously suffer from the lost in the middle problem, right? And methods such as truncation can extend the effective context length of fixed length models such as GPT-4, but such compression methods will lead to performance degradation as the necessary compressions grow. Running MemGPT with GPT-4 and GPT-4 Turbo have equivalent results on this task. So clearly, you can see that. So now let's look at figure 6 to bring home the point. Figure-
On figure 5, I have one question.
yeah.
How is it that MemGPT has a constant output?
Performance.
When you compare other LLMs, it goes up and down, right?
No, what you're saying is in other things, you're literally giving it the entire document. And so if you have to give it like 200 documents, the context length becomes huge for GPT-4. But what will MemGPT do? It won't give it the 200 documents. It will instead go and extract the relevant facts from its utilization will be very small. It will only extract the relevant facts from it will basically rag it. In simple terms, it will rag it.
But what it means is it is uniform, right?
Yeah.
It is not related to the number of documents retrieved at all. The accuracy is constant.
Exactly.
Regardless of the documents size.
Regardless, because it is not ever shoving all the documents into the context. It is just searching into the doc. It is basically ragging it. Searching into the doc, retrieving those pieces of the docs that are necessary to answer this question. We did drag, right? It's literally that. And just giving those little chunks.
The other beautiful thing about this is it is predictable.
Yes, it's predictable.
It's not all over the place and random.
Exactly.
Right. So
exactly.
because it is predictable, it makes for a better reliable agent.
Reliability. And this again proves that when people say, right, oh, context windows is huge, RAG is dead, this is dead, or that is dead, they really don't know what they're talking about. Because if you look at it, look at the accuracy, how badly it degrades. Now, you may say frontier models may have solved some of this problem, the latest frontier models. Even if you stipulate to that, you and I are not going to afford frontier models in our laboratory, isn't it? The best we'll do is a Llama 70B in practical terms. So and also you do it far more cheaply, right? Would you rather pay a million, like for every request, would you rather pay the price of a 2 million token because you're shoving 200 documents into the context window? That doesn't make sense. So, all right. So again, it goes back to systematically thinking, agentic reasoning, and so forth. So let's go back here. Let's look at figure 6. Who won the first Nobel Prize in physics? So this is document retrieval thing, RAG kind of a situation. So archival storage, search, Nobel Prize, Nobel in physics in the beginning, right? So it shows results. The Nobel Prizes beginning in 19 blah, the award is administered by the Nobel Foundation. So what will the machine come to the conclusion? Well, it doesn't have enough facts to answer this question, isn't it? And so what it will do is, it will ask for the second page, right? It is not asking for more results. It's saying, okay, give me the second page of your results, just as you would do in Google, right? If you don't find answers in the first page, you go to the second page. Well, you can assume that each page is, let's say, 13 results. Oh, sorry, 10 of 124 results per page, right? And so you go to the second, and there you get the facts. The Nobel Prize in Physics is a yearly award, right? The 1901 Nobel Prize. So you realize that to answer the question, you need both the pages. Because the first result here, if you notice this, the first result gives you the crucial information that it began in 1901, isn't it? The second result says that who got it in 1901 for physics, right? Etc. And can you guess for what? So that's that. So guys, I can go on with this, but I hope, and there's some more nested key values. I mean, it can also keep facts hierarchically. It doesn't have to keep flat facts. So it goes more into that. But suffices to say that you should realize MemGPT is a good idea. Now, this paper was influential. I'll come to you. This paper was influential. After that, you notice that there was a huge push to incorporate memory into everything, right? So LangChain started including memory. Then now OpenAI, they have a memory feature, right? And so on and so forth. So this has been quite influential. But even if they have a memory, remember, they'll never have it of the same size as this, because here you have archival storage. You have a huge, as much. It basically, document part almost begins to look like RAG. And so your questions was, what was it? What were the prompts? You can read the prompts, right, for the different things. And you can go to the website and see more details, because everything is open source. And you won't find anything extraordinarily surprising. It's just careful planning and doing it. So the beauty of this is, or the key insight in this paper is to say, hey, let's treat the LLM as a processor. And you need a full operating system to harness the power of the processor. You don't just go buy an Intel chip and say, all right, now I should have all my answers. You need a full box, right? You need hard disk memory and an operating system and everything, all the paraphernalia to make it work. And the big message in this, I think the broad message in this is, let's treat LLM as a part of a puzzle, part of a thing that will help you solve problems. Right? So that is this paper. So you wanted to ask a question? Turn on.
Yeah, I have two questions. So if I consider in a practical world, and then if I have a multi-user, and how does it work with MemGPT? So every user is in parallel, they are trying to reach to this an agent. And then if I'm keeping a queue, and then, right, the queue is specific context specific to a specific user. So is there anything that they thought or anything
Yeah.
that's been happening?
What you're basically saying is that if there are multiple of these agents, the question is, who are they talking to? Each agent has its own memory. You realize that this is having a lot of resonance with frameworks like Creo AI. They have memories, et cetera, shared memories, and so forth. So this brings up the more complex topic that in a full-blown teamwork of agents, what is stored in whose memory? And that depends. It depends upon you, how you design it and how you work with it. That's literally it. And that's what you learn. Like as you do this, your projects, right? You will begin to learn what is worth putting in memory, what is worth doing abstractive summary of. So here's the thing, different agents are finding different facts, right? Let's say you want to do SWOT analysis. A market research goes and finds this competitor. Of this competitor finds this. What do you want to do? You want to do an abstractive summary of what exactly are the strengths of your competitors, what is your differentiation, so on and so forth, isn't it? So what will you have to do then? You will not only have to have a shared memory, you will also have to have processes of doing abstractive summarization from those. So one of your agents should be capable of doing that. In fact, your SWOT generating agent should be very good at abstractive summarization.
Right, Asif. I got that context. So far, whatever we learn, AutoGPT or Crew AI, now MemGPT, right? In any of the frameworks, and then we learned that if my agentic reasoning framework with an agent, and then if I'm being, right, continuously being that one single user, yes, actually it serves the purpose. When it comes to the MemGPT, even it's more complex because there is an continuous conversations and then the context. But when I'm talking, whether Prasanna comes and then it's the same server, how does that context actually differentiates between the users if they're touching the same?
You do that. So what happens is that you can see at the end of that, each user is itself an agent in the team. It's just a human agent.
Yeah.
Right. So when Prasanna comes in, when you come in, it's Ravi agent, Ravi human agent. When Prasanna comes in, it's Prasanna human agent. And they all are having a conversation.
Got it.
It's as simple as that.
Got it.
But you will have to remember that a Ravi user agent is not the same. Human agent is not the same as Prasanna human agent. That's all. That's all it comes to.
And when I was been looking at the figure 5 or 7, yeah. So the regular GPT-4 and then 4 turbo, right? Turbo has a generally even 3.5 and 3.5 turbo also. I'm seeing that turbo has more accuracy. What exactly it went in to get that accuracy has been little consistent or little high? Any
Oh, between GPT-4 and GPT-4 Turbo?
turbo? Yeah.
Turbo was literally the next iteration. That's all. Now, obviously, these guys are not very open about what they did. All they do is they just drop it as a message. Typically, I'm told they just put a tweet somewhere that, oh, by the way, we updated our model. They never quite tell us what they do inside. If it was one of the open source models, you could actually know what's there, what's the update. But these people haven't. But you can always tell. See, here's the thing: these companies, right, the makers of these frontier models, at the end of it, they are reading the same research papers, right? So all you can expect is from the day GPT-4 was released and the GPT-4 Turbo was released, just see what developments took place in the field, and they just absorbed it. All right, guys, any questions? I don't know. It does feel a little theoretical, but I hope you realize that this is another exemplar of agentic, how you can reason through LLMs. LLMs are highly capable, but you have to know how to harness its power, right? You don't get this sort of a lift in accuracy from 35% to 93% or 94% without a structural breakthrough, like an important breakthrough in how you think about using the LLM. And this is one way of harnessing the LLM. And MemGPT is considered it's a MemGPT agent. And now there's an open source project. I strongly advise you to, should I bring up the MemGPT project? Let's do that. If all you have to do, and by the way, installation of this couldn't be easier, especially, I mean, obviously I try it on Linux, but I'm assuming that the same true will be GPT. Here we go, MemGPT. This is it, and MemGPT readme. There we go. So getting started, how would you do it? Literally this, pip install PyMemGPT. The only recommendation I would give before this is create a new Conda environment, a new virtual environment. Don't just do it like that. Create a virtual environment, enter that, and then do pip install PyMemGPT. Right. And then all you have to do is MemGPT run. That's it. And you can run it, by the way, with your OpenAI or cloud, etc., or you can run it with your local LLM. Right. So do that, and there are lots of parameters. So you can give it personalities. For example, people have integrated MemGPT with AutoGen. There's a Creo AI version where Creo AI uses LangChain's memory, which is inspired by MemGPT. Here is an integration with the AutoGen. How would you make it work with LLMs? Everything, like it's all there. It's all there. I would. So that's all I have. custom tools. Of course, agents are no use unless you can attach tools to them. Otherwise, they're just conversational things. Right? They talk to you. You don't want it to be that. You want it to actually go do something like Google search, this, that. So like all of these, and it's trying to evolve into a full framework, I suppose, MemGPT. Personalized AI with self-editing memory, etc., etc. I invite you to go read it and play with it, guys, if you can. I'll stop the recording now. Any more questions before I stop the recording?